Assalamu alaikum dear students, welcome back to multivariable calculus series. Today we'll answer a very important question, that how do we apply calculus to vector valued functions? And answer is very simple. We perform calculus on vector valued functions component by component. That is it. So this means differentiation, integration, limits, continuity all work almost exactly as they do for ordinary functions. So by the end of this lesson about section 12.2, you'll be able to find limit of vector valued functions, determine continuity, differentiate vector functions, integrate vector functions, apply derivative rules, solve introductory motion problems. So let's begin with a limit of vector valued functions. So we can define limit of vector valued functions similar to the limit of real valued functions, that if we have a vector valued function rt with components ft, gt and ht, then its limiting value will be a vector L as t approaches to t naught if for every number epsilon greater than 0 there exists a corresponding number delta greater than 0. For all t in the domain, that rt minus L absolute value is less than epsilon whenever t approaches to t naught, that is difference between t and t naught is less than delta. So in order to evaluate limits, the process is easy. You just evaluate the limit of each and every component, and that will be the limiting value of the vector valued function. So let's have a look at the example to understand this. We have this question: if rt is equal to cos ti plus sin tj plus tk, then limiting value of rt as t approaches to pi by 4 would be limiting value of cos t as t approaches to pi by 4 I plus limiting value of sin t as t approaches to pi by 4 j plus limiting value of t as t approaches to pi by 4 k. So after applying limits, we have this, and we know that limiting value of cos t as t approaches to pi by 4 is cos pi by 4, and similarly this will be sin pi by 4, and this is pi by 4. So again, after applying limits and substituting the values, we have this answer. So the process is really easy. Continuity. A vector function rt is continuous at a point t naught in its domain if its limiting value as t approaches to t naught is equal to its value at t approaches to its value at t is equal to t naught. So the function is continuous. It is continuous at every point in the domain. So let's have a function. This is vector valued function. Now since each and every component of this function is continuous in its domain, so this function is continuous. So continuity of vector valued function also depends upon the continuity of components. Okay. Next we have vector value derivative of vector valued functions. So derivative can also be defined by dr by dt, that is derivative of the vector valued function with respect to t is limiting value of rt plus delta t minus rt divided by delta t as delta t approaches to 0. Now let's understand what is r and t and what is rt plus delta t. So let's have a path of rt and p be the point on the path, and let rt be the position vector of this point. Similarly, we have another neighboring point whose position vector is r t plus delta t, right? Now difference of these two is the vector pq, and let's divide this by delta t, and delta t approaches to 0 means q approaches to P. So when Q approaches to P, this vector will be will become this vector, and this is tangent vector. So dr by dt or r prime t is the tangent vector. So which gives us how fast the particle moves. This tells us how fast the particle moves, and it also gives us the direction of the movement, right? So it gives two information: how fast, speed means speed of the particle, and the direction of the particle at some particular point. And evaluating derivative is similar. As we know, we have to apply each and every concept on components. So we'll differentiate component wise. Let's have an example. So its derivative can be obtained by differentiating components like 2ti plus e to the power tj plus 2 pi sine pi tk. So this is the derivative of this function. So as we discussed in previous slides, that first derivative represents velocity and second derivative represents acceleration of the particle. So there are few rules which we need to follow while differentiation, and these are similar to the rules of differentiation for real valued functions, like constant function rule, that is derivative of a constant vector is 0. Scalar multiple rule, it has two parts. First, if that scalar is pure constant, then d by dt of c times ut is equal to c times u prime t, right? But if that scalar is a function of t, that is a scalar function, then we'll use product rule, that is derivative of this times this vector, and then derivative of vector times this function. Sum rule is similar, uh, that is derivative of sum of two functions is sum of derivatives of the respective functions. Similarly, difference rule is also same. Dot product rule is the product rule, but a dot in between the vectors. So the cross product is also same as the product rule, but there is cross between the vectors. Chain rule, if our vector valued function depends upon some function of t, then its derivative with respect to t would be its derivative with respect to ft times derivative of f with respect to t. That is the chain rule. There is an observation or a rule, you may say, if r is differentiable vector function of t of constant length. Constant length means if the length of the position vector remains same with every point on the curve. If this happens, then r dot dr by dt is equal to 0. And this can happen along circular paths. Like if a particle moves on sphere in such a way that its position r is a differentiable function of time, then r dot dr by dt is equal to 0. And you can see along the sphere, magnitude of rt will remain same. So that is why this result holds. Otherwise, in general, this is not the case. So at every point, magnitude of RT will be different. So this is not true in general, but this is true if the vector valued function is differentiable and its length is constant. That is, its length is same along at every point. Integration. So integration, first of all, indefinite integral of a vector valued function with respect to t is the set of all antiderivatives. So indefinite integral is simply antiderivative and denoted by integration of rt dt, that is with respect to t. So if uppercase r vector is any antiderivative of lowercase r vector function, then integration of rt dt is equal to rt plus c. C here is a constant vector. So if we have a function with components ft, gt, ht, then its integration is component-wise integration plus with this constant vector with components c1, c2, c3, and c1, c2, c3 all are constants. Let's have this function, and if we are required to integrate this, then we'll integrate this component wise, that is cos t dt I plus 1 dt j minus 2 integration of t dt k, and this is equal to sine t plus c1, you can write here I. Similarly, this is t plus c2 j and minus t square plus c3 k, right? So this becomes sine ti plus tj minus t square k plus c1i plus c2j minus c3k. So this c1i plus c2j minus c3k is the vector c. So we have to add this vector c whenever we integrate the function and we don't have limits. So in case of indefinite integration, we need to add this constant vector c, just like constant of adding constant of integration in case of real valued functions. So for definite integrals, if the components of the function rt is equal to ft I plus gt j plus ht k are integrable over closed interval ab, then so is r. Okay, so if all the components are integrable, then the function itself can be integrated, and the definite integral of r from a to b is defined by this. That is, we need to integrate each and every component from a to b. Simple. If we have this function, this can be integrated component wise, like cos t dt I plus, this is same as the function we just integrated in previous slide, and similarly this becomes negative 2 0 to pi t dt k. So this is the result. So sine t from 0 to pi, similarly t from 0 to pi, negative t squared 0 to pi, and we have this answer. We just apply the limits and get the answer. So that is all for today's lecture.